Today we shall start limit state method, and we shall start with the topic, our lecture number 6, limit state of collapse, and we shall consider flexure. So, limit state of collapse, flexure, that we shall consider today. So, every method has few assumptions. Whatever method, whatever equation, whatever we consider, so that particular equation or method is based on few assumptions. So, it is true for any experimental setup also. So, whenever you are making any setup which will consider that any real life problem, there also we make certain kind of assumption, and it will automatically will come when we shall consider that problem. So, what are those assumptions? The assumptions here, we shall consider the assumptions that plane sections normal to the axis remain plane after bending. The maximum strain in concrete at the outermost compression fiber is taken as 0.0035. The strain is 0.0035, that is the maximum limiting strain in concrete that we shall consider, that is 0.0035. The tensile strength of the concrete is ignored. So, that is the almost you can say primary assumption in our concrete design, reinforced concrete design. We are assuming that we shall not consider tensile strength of concrete. The stress block may be assumed to be rectangle. I shall come within a minute what is stress block. The stress block may be assumed to be rectangle, trapezoid, parabola, or any other shape which results in prediction of strength in substantial agreement with the results of test. So, even if you consider a beam, and that beam if you test it, whatever the failure load you are getting, and whether with your model you are getting that result, with your model whether you are getting that result, then you can say that it is in a good agreement with your experimental result and the method you have proposed, the stress block you have proposed, that is valid. The next assumption, the stresses in the reinforcement are derived from representative stress strain curve for the type of steel used. So, the stress strain curve for steel, that also you have to consider. I shall show you a graph. For design purposes, the partial safety factor gamma m, that is for material, that partial safety factor for steel, we consider 1.15. So, if FOI is the stress, yield stress, so we have to consider FOI by 1.15. We have to consider FOI by 1.15, that we have to consider. That is the, for design purposes we shall consider. We never take the ultimate limit for our design calculation. The maximum strain in the tension reinforcement in the section at failure shall not be less than FOI by 1.15 ES plus 0.002. So, FOI by 1.15 ES plus 0.002. This is your that strain that should not be less than this value. So, for different grade of steel we shall get different limiting strain. We have three types of steel: Fe 250, Fe 415 and Fe 500. Most of the cases we use Fe 415, and mild steel we use it Fe 250. According to IS 456, this is your strain and stress strain curve of plain concrete. What we consider here, please note the strain. There are two strain, one is 0.0035, which I have already told, which is specified in the assumption and given in IS 456 2000. So, that you should remember that 0.0035, you should remember 0.0035, that is the limiting strain, maximum strain allowed in concrete, plain concrete, and for design purposes we shall use this curve. What we consider, this is the one that cube strength, M20 20 Newton per square millimeter, M25 25 Newton per square millimeter. We shall take 0.67, that means 2/3 of that cube strength or characteristic strength we shall consider for our design purpose. Further we shall consider this value, that is 0.67 FCK, and 0.67 FCK divided by gamma m. Gamma m, that is partial spectrum factor of material concrete. Gamma m for concrete we shall consider 1.5, gamma m for steel we shall take 1.15, and which is justified because we are considering, we take steel that is manufactured in the workshop in the controlled environment. So, obviously we can take less, but whereas concrete that is made in the field itself, so we are taking a little bit higher, and that one we are considering, we are taking 1.5, and that curve you will get it in figure 21 for your reference in IS 456. So, one more thing I would like to point out, this part is parabolic and other part straight, but in real situation, that if you do the stress strain curve, or if you do the experiment, if you apply the load, you will get certain drooping portion also. That means it will go up, this way it will go up, then slowly it will come down like this, it will go certain level. But we are not considering for our design purposes. For our design purposes, we are taking this curve, and when we shall take the actual value, design value, we shall consider this curve, which is based on this curve we are getting from the experimental result, experimental data. Then we are taking 2/3 of that. Further, we are dividing by partial safety factor for materials, and then finally we shall get the curve for our design purpose. Figure 23A of IS 456, that is for cold work deformed bar, high strength, and we shall consider ES, modulus of elasticity for steel. We shall take this value. So, we shall take this value, and we can get the different, for different strain we can get the stress value. So, we shall consider for high yield strength deformed bar, for high yield strength deformed bar we shall take this stress strain curve for steel. This is figure 23B, steel bar with definite yield point. For mild steel we shall consider, we shall take this curve. This is the test data, and this is after dividing by partial safety factor. So, let us come to the limit state of collapse. We are starting with limit state of collapse, ultimate strength. and we shall consider bending, flexure. Further, we are considering that singly reinforced section. So, let us draw a cross section of the beam and we are having area of steel d, effective depth small d, and though we do not need right now, we do not need capital D, but even then let us write down for the completeness. This is your capital D. We have width of the beam small b, and we should have the neutral axis. Let us draw it here also further, so that we can draw the stress strain curve. This is the neutral axis position from the maximum compressive stress. We shall get the compressive stress at the top fiber, that is maximum, and from there we are measuring the depth of the neutral axis, which is defined at x. In working stress method, we have not considered, we have not taken the strain criteria, but in limit state method we are specifying the strain, that is the limiting value of strain that we are specifying. For concrete, the limiting strain 0.0035, that you should always remember, 0.0035. We shall go up to the that steel position. This is 0.0035, and this value, say epsilon s, let us say this value epsilon cu. What about the stress block? The stress block comes the same one which we have shown you, that curve. We are having maximum 0.0035, somewhere here 0.002, because we are starting from 0. So, somewhere we shall get 0.002, finally we shall get the maximum strain allowed 0.0035, which will never go beyond this 0.0035. According to this curve that mentioned in the code, we shall consider this curve. This is our stress block also. This value comes 0.45. We shall consider this value as 0.45. So, we are taking 45% of the cube strength. To be more specific, I can say I am taking 45% of the cube strength. For our design purpose, we are taking 45% the cube strength. What about this steel? This one will be 0.87 FOI multiplied by, let us write down here, please allow me, times AST. 0.87 FOI AST. Here I think it is better if I repeat once more here. 0.87 FOI, that is the stress permitted in steel multiplied by area of steel. This one, that your T. So, tensile force T on the steel 0.87 FOI AST. We shall get the compressive force, that is C. What is the our interest here, that beam which is under bending, under flexure, how much maximum load it can take, what is the moment carrying capacity of that section, that is our target. If we can find out that value, then we can say this section having this many number of bars and the cross section, that width and depth, we can say this is the maximum moment carrying capacity, and that we have to find out. So, if we can find out that one, then from analysis the result you have got moment, different moments you have got in different places. So, you can provide your section. That way also you can do in other way also. That means you are taking a particular section, let us see the moment carrying capacity and let us provide. It should be always, it should be more than the computed value, the moment at that particular section. This is lever arm. We specify by Z. So, lever arm Z. So, what is the difference here? In working stress method, we shall not always compare with the working stress method, but since we have done in the last class that working stress method, let us compare for this singly reinforced section for flexure. We shall, here we are considering, we have started with the strain. In working stress method we have not considered strain, we have not taken strain. Only difference is the stress block, only difference is the stress block. In that case stress block linear, here we are getting certain portion parabolic, certain portion straight, but otherwise your formulation everything will go in the same direction. Here also we shall consider the same lever arm, and it should be in equilibrium position, compressive force equal to tensile force, and moment carrying capacity nothing but compressive force times the lever arm or tensile force times the lever arm. Only that difference, the stress value, that portion is different. It will be different for this case because we are starting from the strain diagram. Epsilon SU as per the code, to repeat, FOI, that is one of the assumptions also. Or we can write down in a familiar way, which is nothing but 0.87 FOI, or let us write down so this is our corresponding strain. This one will be epsilon SU, sorry, this one will be epsilon SU, that ultimate strain in steel. We are considering singly reinforced, only reinforcement in the tension side, and we know that 0.0035 is the limiting strain in concrete in compression. We shall get the corresponding epsilon SU. For different grade of steel, we shall get different limiting strain. We shall get different limiting strain. Let us draw once more the stress block. The strain, and also draw the strain here. The strain here 0.0035. This is 0.002. So what about this value? This one will be equal to this value. Let us find out 0.002 by 0.0035, and which will be 0.57. If we take depth of the neutral axis from the maximum compressive stress side x, this is 0.57 x, and this one 0.43 x. So 0.57 x and 0.43 x. We can write down total compression C area of rectangle, the full one, minus area of outer parabola. Area of outer parabola means this portion. Equal to 0.45 FCK, 0.45 FCK, this one multiplied by the neutral axis. To make it separate out, let us give a parenthesis. It is not multiplication 1, x is the depth of the neutral axis, multiplied by b minus 1/3. We have to find out this area, 0.45 FCK, this one also 0.45 FCK, multiplied by 0.57 x, multiplied by the area, width b. The b is the cross sectional width, which equals 0.45 FCK x times b minus 0.86 FCK x b equals 0.364 FCK x b. We take this 0.364 FCK x b. X is the depth of the neutral axis, FCK the characteristic strength, b width of the beam 0.364. This 0.364 we can take as say one factor, that K1 we can also write down equal to say K1 FCK x b. This is one factor generally considered, that K1 FCK x b. We can further we can write down as say C equal to, I have told K1 FCK x b, in our case 0.364 FCK x b, where K1 equal to 0.364. We write down the equation in a different form, x by d multiplied by bd. So 0.364 FCK x by d, this is multiplied by bd. Bd is the cross sectional area. Please note we are taking d as the effective depth, not the overall depth. Always we shall take BD whenever we consider, that is the effective depth we shall take. For area of steel or percentage that steel, we shall consider AST by BD, B width and D effective depth. Please note we shall always take D effective depth. Let us write down once more the stress block. .43x, 0.57x, compressive force. We shall add one more factor, that is K2 times x. X is the this depth. What is the factor K2 that we shall find out? We shall take moment. We shall take the moment about the neutral axis. This is our neutral axis. If we take moment about the neutral axis, already we have computed that C 0.364 FCK XB, that is the total force. Already we have computed that. 0.364 FCK XB, this is one term, that is the total force, and we are taking moment about this line x minus K2x, which is equal to 0.45 FCK XB times x by 2. The total rectangle 0.45 FCK times x, the total rectangle, and CG width and x by 2. So, we are getting that total rectangle minus 1/12, let us make it x whole square b. If we take that area, so we are taking out this parabolic portion, area times that CG. So, we shall get this one, which equals 1 minus K2, if we simplify it, equal to 0.584. For K2 equals 0.416, or we can say, let us say 0.42. So, the compressive force will act from the top fiber having the maximum compressive stress from there at a distance of K2x, which is nothing but 0.42 x. So, we have got one factor K1 and another factor K2. Depth of neutral axis of a we shall get it from the again from equilibrium of forces. Total tension T FST times AST, stress times AST, total compression C equal to total compression C equal to, we have derived here to show you total compression C equal to 0.364 FCK XB. So, let me copy it here, 0.364 FCK XB. Therefore, for equilibrium case, we also write down, instead of writing 0.364, we also write down as 0.36 also. We can take it because that way we are estimating little less, we are taking little less. So, that also we consider. So, let us take 0.36 FCK XB. Let me underline that we have noted down 0.364 and here 0.36. We are taking little less value. FST AST x equal to FST AST divided by 0.36 FCK B. We can also write down other way also. We can write down this one as x by d equal to FST AST 0.36 FCK B times d. we write the equation in this fashion, that x by d, we instead of directly computing that value, we specify in this ratio that x by d. So if we know FST, we can find out that x by d ratio. We can find out x by d ratio. Now if we take the section is under reinforced, if we take section is under reinforced, that means we shall reach the yield stress in steel first. In that case, FST will be equal to 0.87 FOI. That is the permissible stress according to IS 456. So we can write down the equation for under reinforced section. FST equal to 0.87 FOI XU by D. We are giving a special name XU, that is the XU is the ultimate, that you can say that depth of neutral axis, you can say XU by D equal to 0.87 FOI AST by 0.36 FCK BD. Let us check limiting values of x by d specified in IS 456. Epsilon SU equal to FOI by 1.15 ES plus 0.002, where ES equal to 2 into 10 to the power 5 Newton per square millimeter. XU by D equal to epsilon Cu divided by epsilon Cu plus epsilon Su. Where from I am getting? I am getting from the strain diagram. This is epsilon Cu and this one epsilon Su. Epsilon Cu, epsilon Su. So we can get, let us say this one XU and total depth D. So we can find out from this curve, from this similar triangle principle, we can find out XU by D, epsilon Cu by epsilon Cu plus epsilon Su equal to epsilon Cu we know, which is nothing but 0.0035 divided by 0.0035 plus epsilon Su. Epsilon Su is different for different grade of steel, and which we shall get it, which is given in our IS 456, we can get using this formula. So limiting values of x by d. Limiting values of x by d. Type of steel, mild steel, high yield strength 250, Fe 250, Fe 405, Fe 500. Using the formula, we can get the yield strain 0.0031 for Fe250, 0.0038 for Fe415, 0.0042 for Fe500. Simple calculation from there we can make, and we should remember, at least we should remember 0.0038. So please note for concrete 0.0035, most of the cases we use Fe415, so we should note the limiting strain which is nothing but 0.0038. At least you should remember these two values, 0.0035 for concrete and for the steel maximum used Fe415 0.0038, and we can get the limiting values XU by D 0.53, 0.48, 0.46. So from that equation we can get it 0.53, 0.48, 0.46. So again you please note this value 0.46. XU by D limiting value 0.46 when Fe415 is used. We shall consider, we have already derived this equation C equal to K1 FCK x by D times BD. These two should be suffix. So K2 times x is the distance of the center of compression in the concrete from the top compression fiber. That I am repeating number of times. So K2x, so one parameter is K1, the other parameter is K2, and the third one, the maximum or limiting value of compression, F times FCK BD. So one parameter K1, another parameter K2, and the third parameter we are taking F. So values of constants for maximum compression block. So we are considering that is as a block, that one straight portion, another one parabolic portion we are considering. For different steel, that already we have noted down, XU by D that we have noted down 0.53, 0.48, 0.46. K1 that is 0.364, that is constant for steel, that K1 value. Similarly K2 also same 0.42 for all the cases, and F that is 0.192, 0.175 and 0.167. for different steel we are getting different limiting value. We shall get these values, we shall get, and we should at least we should note down again 0.175, that at least we should note down that 0.175. Let us take, we are deriving those things for our limit state method. Our objective here, let us derive that how far we can go and what are the things we require for design purpose when we are considering say singly reinforced section, and for limit state of collapse for flexure. Expression of resistance moment for a balanced section in terms of FOI, that is steel and percentage of steel, the steel stress and percentage of steel. XU by D equal to 0.87 FOI AST divided by 0.36 FCK BD, that we have already got it. Mu, that limiting moment, that resisting moment, moment of resistance, 0.87 FOI AST, this is the tensile force multiplied by the lever arm. So, lever arm here equal to D minus, we can write down 0.42 or 0.416 also, the exact value also we can write down. Let me repeat once more here. And somewhere here that compressive force C, this one we are talking 0.416 or 0.42 also we can consider. And lever arm, this is your lever arm equal to D minus 0.416 0.87 FOI AST divided by 0.36 FCK times B. We are getting this XU, we are putting it here and we can find out the lever arm. We can write down it as D minus 1.005 times FOI AST divided by FCK B. We can take this one, instead of going to that precision 1.005, we can simply take it as just 1. In other way, we can write down this one as D minus FOI ST FCK times B. Therefore, mu will be equal to, this is your lever arm. Therefore, mu equal to, we can write down 0.87 FOI AST times D, we are multiplying the 1 minus FOI AST divided by FCK times BD. 0.87 FOI AST D times 1 minus FOI AST by FCK BD. Mu, that is the moment of resistance, that resistance moment, that is section having area of steel AST. We can get from this formula, we can get that moment of resistance. Therefore, we can write down it as mu 0.87 FOI. Let me copy it once more. Mu equal to 0.87 FOI. P, that percentage of steel, I can write down it as AST by BD into 100. This is our percentage of steel. So, we can write down mu equal to 0.87 FOI. AST, we can put it from here So, we can write down it as P by 100 1 minus 1.005 Fy by FCK P by 100 B d square. We generally write down in this fashion mu by B d square equal to 0.87 Fy P by 100 multiplied by 1 minus, here again I can omit this 1.005, ignore that, Fy by FCK is P by 100. So, for a particular grade of steel and percentage of steel given, we can find out that mu by Bd square, where we do not need the section size, we can get one value. That means one can plot it also for different P also we can plot it also. So, we can get mu by Bd square, we can get it. For different percentage of steel, we can get the corresponding mu by Bd square. So, we can plot it also. And from here, if we know this value, then multiply by Bd square, we can get the corresponding moment of resistance that we can find out. One thing here I shall tell you, we can also find out for other cases also. Just to repeat the one which we have specified in your mentioned in the working stress method, that is your balanced sections. So, sections in which the tension steel reaches yield strain simultaneously as the concrete reaches the failure strain in bending are called balanced section, because we are considering beam and that is mainly for bending, the dominating one. So, we shall consider that section as balanced section when concrete and steel both of them simultaneously reaching the limiting strain, specified limiting strain, then we shall take it as balanced section. Similarly, we have under reinforced section, and which is preferable. Most of we always prefer this one. So, sections in which tension steel reaches yield strain at loads lower than the load at which concrete reaches failure strain are called under reinforced sections. So, in this case the load applied, we can apply the load, we shall stop. When we shall stop? We shall stop when we shall measure the strain, we shall find the strain in the steel that is achieved say 0.0038 for Fe415. We can measure the strain and we can find out 0.0035, and then we can stop there. We shall not consider that concrete, maybe the concrete still we have not reached that value, and that one we shall take it as a under reinforced section. Similarly, we have the other side also. So, sections in which the failure strain in concrete is reached earlier than the yield strain of steel is reached are called over reinforced section. So, we are having balanced section when we have reached the strain. Compared to working stress method, we consider that one from the stress point of view, but here we are considering from the strain point of view, because we are checking the strain and then from the stress strain curve we are getting the corresponding stress. So, this is the basic difference with the working stress method and the limit stress method. And we are having balanced section when we have reached simultaneously, and obviously there are two options only, either steel reached first or concrete reached first. If steel reached first, then under reinforced. If concrete reached first, then we shall consider as over reinforced. And over reinforced section is not preferable, because if it is under reinforced section, then it will give, it has it will deform, actually it will have some time to deform, it will yield for some time. So, occupants will get some time to that vacate that particular, say, your place. So, we can say that under-reinforced section is preferable. We can also get that one from the limiting XU by D. The XU by D which is given, from there also we can find out the limiting value. In no circumstances we should not that go beyond that XU by D value. It should be always within that limit, that XU by D. From there also we can check that whether it is over reinforced or under, whether we are getting that yielding in steel or not, that also we can find out. Just to conclude this session, we shall say that percentage of limiting steel areas for balanced design, we can find out the derivation, other things I shall give you in later stage. We can find out for different steel the XU by D or X by D, whatever you say, and the percentage of steel. Instead of percentage of steel, we have written this one PT Fy by FCK. So, that is equal to 21.974. From there we can find out the corresponding value of PT. So, similarly for Fe415 also we can find out. Similarly for other one also we can find out. Okay. So, we shall conclude this particular class here, and we shall continue the next.